Hello, welcome to the Salmon Recovery project presentation. We are the UW-Tacoma MSBA program Team A4, working with the Washington Department of Natural Resources. I'm Kelly Roberts, lead project manager. On our team is Lucas Forrest, who created our statistical model. We have Anderson Kim, who built the Power BI dashboards, and Suprita Bamkar, who developed our mobile app prototype. Many people in our region are aware that local salmon populations are threatened and endangered. This has been an ongoing issue for decades. What's not so apparent is the scale of the problem. There just isn't enough funding to make change everywhere. To address this issue, our team has created visualization tools to help the DNR manage resource allocation. We use data from research scientists at the UW School of Environmental and Forest Sciences to focus on the Snohomish watershed, Water Resource Inventory Area 7, with the capability of expanding to analyze watersheds statewide. For our project, we started by importing an Excel file into R for processing. In the future, this code could be updated to pull data directly from an SQL server if the data is uploaded to an SQL server for storage. The imported data is split into 4 data frames, one for specifically 2007 data, one for specifically 2019 data, and one for identifying information such as the parcel ID and location. We do not reorder the records in our datasets at any point in the model, so the identification portion can be split off and added back in later without risk of mismatching the records. Our final data frame collects fields that appear in both the 2007 and 2019 data. These fields are not subject to frequent changes, as they represent proximity to roads, other forest land, and rivers. Due to limitations in data availability, these fields are the same for both 2007 and 2019, which makes our model subject to overfit, as some training variable data are the same as our predicted variable data. These values are not expected to vary dramatically each year. The likelihood of these fields causing a major discrepancy in the results is minimal. However, the future updates to the dataset could work to update these fields to improve the model's predictive accuracy. Variables were renamed to facilitate ease of understanding and provide users with a standardized naming format, which helps improve user comprehension of the model variables and what they represent. Users can easily filter out specific types of recorded data if they choose to adjust which variables are brought into the models. During the model exploration phase, we noticed that most of our data needed to be scaled and transformed. This is expected with land parcels, where the vast majority are small, but the possibility of very large parcels also exists. We decided to use log+1 transformations, followed by scaling the data using R's scale function. For our analysis, we decided to use the ensemble methodology to determine which parcels of land are most likely to be converted in the near future. Using different classification models is like having a group of advisors that each have different criteria they use to determine which parcels are at risk. They come to a consensus, and the score is presented to the viewer in the dashboard for interpretation. Using ensembles helps us lower the predicted error variance of the overall model, which helps us generate more precise predictions. Currently, our ensemble method gives equal weighting to each model's classification. However, in the future, more work could be done in determining if models should be weighted differently. The downside to the ensemble method is in increased computational need. Each individual model needs to be run before combining the model conclusions. We have spent time optimizing these methods so that the computational need is not too large. In the future, running the R code separate from Power BI would be beneficial, as the computations can be done once, with the output file imported into Power BI separately. Once the models have all calculated their classifications and the consensus has been recorded, the model creates a separate data frame that combines the model classifications, consensus score, and identity information, passing this output into Power BI for analysis on the dashboard. For deployment, we created 2 Power BI dashboards. The Descriptive Analytics dashboard uses visualizations for data understanding and identifying key land parcel qualities. Our Predictive Analytics dashboard uses output from the R code to assess risk scores and identify land parcels of greatest interest. Our Power App is a mobile app prototype that can be used in the field. Going forward, we recommend the DNR use the visualization tools we've created to help manage resource allocations. That means creating a list of small forest landowners at risk, then using the list to recruit those small forest landowners into DNR programs so they can offer resources. We recommend they use the tools we've created to expand analysis for watersheds statewide. We recommend the DNR continue collaboration with the UW School of Environmental and Forest Sciences. That is, to follow their research methods to acquire new and updated data. We recommend they maintain the model and visualization tools we've created by reviewing the model fit and acquiring updated and new data. Finally, we recommend they leverage community resources, combining Washington State tech and salmon cultures to innovate salmon recovery efforts. They could consider sponsoring local events like case competitions and hackathons, possibly working with organizers to create challenges for participants. That might mean students from different programs like the GIS program or experts within the DNR. Our final recommendation is to follow up with an MSBA applied project next year to expand the capability of these visualization tools for statewide use. Now I will hand the presentation over to Lucas to demonstrate our visualization tools.
Welcome to the demonstration portion of our presentation. My name is Lucas Forrest, and I'll be guiding you through the dashboard we created for the Washington State Department of Natural Resources. Our dashboard consists of 2 different views, a descriptive view, which shows key land parcel qualities, and a prescriptive view, which integrates our classification model's risk consensus. We're currently in the descriptive dashboard, which contains a map of parcels by their respective land use categories. Each dot on this map represents a single parcel of land, with colors describing the land use and size representing the total acreage for the parcel. To the right of our map, the bar chart gives us a count of each parcel land use category. A total of the land parcels currently selected is shown near the upper left corner of this bar chart. For those of you who may be unfamiliar with Power BI, these items are all linked and automatically changed to represent the parcels that are selected using filters or individual point selections on the map. The interactive nature of Power BI allows users to quickly focus on only the parcels of land they deem relevant to their analysis. There are 8 sliders on this dashboard, which allow the user to quickly filter by certain features. In the lower right of the dashboard, multiple proximity sliders can be used to adjust proximity to nearby features, such as roads or types of land. The similar ownership slider adjusts for acreage size based on parcels with similar owners. In the upper left, the user has the option to filter to only parcels that have a certain percentage of forest coverage, or by the number of acres in a parcel. The Washington Department of Natural Resources may want to focus on a specific subset of these parcels for their programs. Searching for forest or natural land between 75 to 200 acres, but over 50% forest land, is as simple as adjusting the percent forest slider to 50%, adjusting the forest acreage to a minimum of 75 acres and a maximum of 200 acres, and finally, by clicking Forest or Natural in the bar chart on the right. The table in the lower left corner of this dashboard can then be exported to Excel for further analysis. We will now move on to the prescriptive view of this dashboard. which helps us understand the conversion risk of each parcel, which is based on a consensus score from our model. Our model uses several classification techniques that each determine whether they believe a parcel will be converted. These individual decisions are added together and presented on a scale of 0 to 10. 0 indicating no individual classification methods expect a parcel in question be converted, and a 10, which indicates all models think the parcel will be converted to non-forest land. Like the descriptive dashboard, the primary focus is on a map of all parcels. Each dot on this map represents a single parcel of land, with sides representing the total acres for the parcel. However, on this map, parcel color is determined by the parcel's consensus risk score. At the top of the dashboard, users can select consensus scores from the drop-down, which focuses the map on those parcels. The number of selected parcels is shown under the selected land parcels count. In the upper right of the dashboard, there are two gauges which show the average consensus score for the selected parcels and the average number of acres in the parcels selected. If the Department of Natural Resources wants to figure out where they should focus their efforts, they can look for hotspots on the map. We can demonstrate this by first clicking through our consensus levels to determine if there are any visible hotspots. While consensus levels 4 and 5 don't show us any visible patterns, once we click through consensus 6 through 8, we see what looks like a cluster of properties near Monroe. To look at this area, let's use the drop-down to select risk levels 5 through 8. Without the other levels crowding the map, this cluster becomes more obvious. We can then zoom in on this area and individually select each of the parcels that we believe to be a member of this cluster. After we've done this, we can see that the 24 selected parcels have an average consensus score of 5.92 with an average acreage of approximately 43 acres. Looking at the lower right selection of our dashboard, we can see a visual representation of the parcels and their overall place in the consensus model. It appears that most of our consensus level 8 parcels are actually in this cluster, but most of these parcels have a lower score, with the majority being 5. However, if the level 8 parcels were converted, it is possible that these other lower ranked parcels may increase in risk, as development in a certain area often expands to the surrounding area as well. Now that we've found the area that we wish to focus on, we can once again export the parcel data using the table in the lower left portion of this dashboard. This concludes the demonstration portion of this presentation. In the next portion, I will briefly discuss proof of concept work we have done to create a mobile application that can interface with this dashboard. This portion of our presentation will cover the proof of concept Power App that we created for mobile devices. This app can be used to display data on parcel and visualizations that are created from the Power BI dashboard we just demonstrated. Power BI initially processes the data from our dataset. Once ready, this data is passed on to the Power App, which can review this information. This app also allows the user to write comments for parcels, which are then sent to the data source for storage. The direct integration with Power BI allows the Power App to always have up-to-date information from the dashboard, allowing users to use this data in a field environment. Currently, the proof of concept has two views. The first view takes a user to a list of all parcels and displays their associated consensus risk level. Selecting one of these parcels gives the user additional information about these parcels and the ability to add a comment regarding that parcel. As there are thousands of parcels, the ability to search for a specific parcel number is available at the top of the parcel selection screen. This view could be updated to show additional information or add additional methods for users to filter their search. Our second view takes the user to an interactive map that contains all parcels from the dashboard. This allows the user to have a visual representation of the location of these parcels and to interact with the map, similar how they would be able to use the main dashboard. In the future, filters would allow the user to filter out certain consensus levels or to select all parcels in a certain area. On behalf of all of the members of Team A4, thank you for attending our presentation.